Hi everyone, I hope you're having a good day. And I'm catching up on answering questions and making a plan, and I also want to work on the grade book. It's getting there. We're going to get an approximate for definite integrals, or approximating definite integrals. And by the way, I'll make sure that we have a review for the test and also a review for the final. Okay, this section. So before we get into, I guess, the main topic from this book, you can approximate integrals with the right side of the intervals or the midpoints or the left side. We're going to use the midpoints. And also, this technique is good for integrals that are like impossible to integrate with like the rules that we've learned so far. It's also used for a function, a function that cannot be written up as a formula and all you have is data. Or let's see, a function. Okay. And I tried to talk about this earlier in the semester, but now we're actually going to do it. And we're going to talk about the overall idea, break it down into steps, do examples. Okay, so we're doing the midpoint rule. All right, so if your function f of x is positive, greater than or equal to 0, or your function is above the x-axis on the interval AB, then the integral from a to b of f of x dx is approximately, so we're going to do this symbol, the sum of f of x sub I bar, which we'll define in a sec. F of x sub I bar multiplied with delta x. And we're going to go from I equal to 1 and up to n. And again, when we work on our examples, we'll see that this will be a bunch of rectangles added together where this is the height and this is the base. Okay. So first of all, delta x. What's that? Okay, this is b minus a and then divide by n. X sub I bar. This is a symbol for midpoints. So the first midpoint, second midpoint, up to the nth midpoint. We'll take x sub I minus 1. Add. So x in the subscript is I minus 1. X subscript I divide by 2. So take the size of each of your intervals, add them together, divide by 2, and that's the midpoint for that interval. That's just this piece right here that we're talking about. Then we'll put that into the function and break it down in steps in just a minute. Okay. So I have a sketch and it will help with steps. All right, so your x-axis. And we're going to go from A to B with some function. We'll do a straight line. So between x sub I minus 1 and x sub I is this midpoint. We call this first value x naught, x with a subscript 0. Last one's going to be x sub n. Let's say we have an interval right here from x sub I minus 1 to x sub I. Right there is x sub I bar. Got kind of messy. Okay. Steps for finding or for approximating the area under a curve using the midpoint rule. Oh, actually, let's keep on talking about this sketch. And also, yeah, let me see what my video settings are like. Oop. Okay, because it's mentioning that it's blurry. Is that any better? No, I don't know. Let's see. I'm going to change it back. Okay, let me, well, also it could just be my screen, so let's try that. And then also just write bigger. Okay, let's just do this again. Oh, okay. Okay, here we go. And bring it in. And then maybe even closer. Actually, it's, how are we gonna? I want this whole thing. Ah, okay, there we go. So we're gonna go back to the drawing. This space. Okay. This is X naught. And the last one we call X sub n. We have a function from here to here called f. And then we're going to break up the interval from a to b into subintervals. And I'm going to slice it up like this, let's say. We talk about this interval, which we'll call the interval that goes from x sub I minus 1 to x sub I. Okay. And then in the middle of that, or where we have a midpoint in that interval, we're calling x sub I bar. So we're going to make a rectangle from x sub I minus 1 to x sub I. And use the midpoint for the height. So take that midpoint up to your function. And then from there, go straight over and across. Okay, then we'll find that area. And add it to the area of the other rectangles. So let's draw another one. From the previous interval, we would find the midpoint, go figure out the output for that point right there. And that's the height of your rectangle. So go over and over and down. And we would just like have a rectangle for each interval, add all the rectangles together. Okay, so let me know if you need something like rewritten, if it's hard to see. Try to draw this, draw these pictures nice and big. Steps. First step. Break the interval into n subintervals. Or divide the interval AB. each with width delta x. After that, find the midpoint of each interval. So keep on continuing this back to the top. Okay, so find the midpoint of each of the intervals of the n intervals. See. And you don't have to be that great. And I'm going to write down what that value is. It's called x sub I bar. And you take the beginning of the interval, add it to the end of the interval, and then divide by 2. So x sub I minus 1, add x sub I. Find each of those midpoints, and also the values of I are between 1 and n. Evaluate the function at each midpoint. And build n rectangles. Each with width delta x and height of x sub I. Okay. Okay, a height of f of x sub I bar. Okay, and the width of, let's see, delta x. Okay, cool. Well, we made it work. All right, after that, approximate the area under the curve by adding the area of each rectangle together. Okay, so actually find those midpoints, create your rectangles, and get those areas, add them together. Areas of the rectangles. Last part. Okay, then I'm just going to write that out mathematically. We're approximating the area under the curve, so we're going to take the integral from a to b of f of x dx. Have it approximate to the sum. So adding all those rectangles together is a sum. Oops. From I equals 1 to n, of the height of the rectangle, f of x sub I bar. Times the width of the rectangle, delta x. Okay, that's, I think it, except that's it for the steps. So as you increase the number of rectangles, you get closer to the actual area under the curve. And then we can define a definite integral as a limit of a sum. I wrote, to be more accurate, increase the number of rectangles. And then we can write the integral from a to b. We'll make it nice and clear. So then dot, dot, dot. So we'll take this and have n go to infinity and just fill that in with an infinite number of rectangles. The integral from a to b of x dx equal to the limit as n goes to infinity. That sum from I equals 1 to n of f of x sub I bar delta x. Nice. Now we have examples, and I think we'll get through at least 2 of them. We're going to let f of x equal x cubed. Use the midpoint rule. With n equal to 2. So we're going to build 2 rectangles and add their areas together. Okay, so we're using this to approximate the area under the curve on the interval from 0 to 1. Okay. So this one we can start to draw a sketch of. First part though is let's find delta x. Okay, so we want to take 1 and subtract 0 and divide by n. 2. Okay, our function is x cubed, which goes up and over and up again. So we'll draw part of that. Then flattens out and comes back. Going from 0 to 1. And the width of our intervals is 1/2. So from 0 to 1/2 and 1/2 to 1. But we're going to use midpoints. So between 0 and 1/2, find the midpoint, 1/4. And this will be as 1/4, 2/4, 3/4, and 1 is equal to 4/4. So just to get used to the notation, the first midpoint we call x sub 1 bar. And that was 1/4. Okay. The other midpoint we need, midpoint number 2, is x sub 2 bar. Which is at 3/4. But we want to evaluate the function at each midpoint. So put 1/4 into the function, put 3/4 into the function, and that will give you that height right there. And then the other midpoint goes up to the function and gives you the other height that you need. Let's go ahead and draw the rectangles first. So we're going from 1/4 up to the curve and making a rectangle with that as the height. Okay, then the other rectangle has a height of f of 3/4, so that's the top. It comes down. Okay, f of 1/4. Will be 1/4 cubed, which is 1/4 cubed, which is 1/64. Okay, put in your other midpoint. Be 3/4 cubed. So we have 3 cubed over 4 cubed is going to be 27/64. And I think I just started to put everything together after that. Yep. So we're going to write that the integral is approximately the area of this rectangle added to the area of that rectangle. Okay. And let's go ahead. We're going from 0 to 1 of x cubed. Actually, no worries. So hopefully you got this one. F of 3/4 is 27/64. Okay. So this is about I just wrote it as like that height times base of the first rectangle. So it's a height of f of 1/4 times the base, which is 1/2. Okay, plus the other base times height. we figured out those numbers. 1/64. Add the other area of the rectangle, which was 1/2. 27. And I'm going to jump to what I got. I got 7/32. So this is actually an integral that we could do, and you could evaluate this integral with what we've learned so far, compare it to that number, and see how close those numbers are. But I think that we're almost out of time. So next time we'll do some more challenging functions and then start the next section. Okay, so we'll come back and do more examples on Monday.